Is it red bin day or blue bin day? Or maybe you'll forget to put the bin out entirely. In this video, I'll show you how to make an internet-connected device which will connect to your console and show you which bin is due for collection next. It does this by changing colour. So if it lights up red, then you know it's the red bin that's due. I posted a picture of this project on Twitter and to my surprise it went viral. I got millions of views, hundreds of replies, and people seemed really interested in it. I ended up being featured on national TV, radio, even in print. People who wanted one suggested I sell them directly, but for reasons I'll go into later, I needed a certain number of orders to make it viable, and that's why I had a Kickstarter for it, but that didn't reach its target. I always planned a tutorial for this, so here it is. Now you can make your own. You can also win one, or the parts to make one. Since I've got a couple of spare bins lying around, I've decided to give away everything you need to make your own, consisting of the 3D printed parts and the electronic components you'll need. If you want to win one, then subscribe and leave a comment below and I'll pick somebody at random. Sorry, this competition is for UK people only. So first things first, here we have a 3D bin. This is a bin I modelled, other bins are available. It's pretty simple. There's two pieces. This is not necessarily the same design that would have been 3D printed, would have been injection moulded if the Kickstarter had gone through, but this is kind of optimal for just assembling yourself and 3D printing. So that's the model. That's one of the things you need. I'll put a link to that, those two things. The other thing you need is what I call a baffle. I still need to clean some of the stringing from this print. But this is a light baffle for the inside. You can't just put LEDs inside an object like this and have it light in a pleasing way. It would just look washed out and strange. So what these do is they kind of help spread out the light, and also they separate the colours a little bit for when you have multiple colours showing. So that's the 3D printed things. Now let's talk about the LEDs. These are what are called Neopixels. So I've got 4 here. You can have less or more or whatever. You daisy chain these together so you can have quite a lot in a string, and they only take 1 pin on the microcontroller to actually control, which is excellent. So there you go, that's the lights, that's the model. Obviously you need some wire. Here I've got some solid wire. I will also be using stranded wire. So you need some wire, I would say here you go, red and black. Then you also need a resistor, 330 ohms resistor. Now we need the microcontroller. I will explain a little bit about the microcontroller from an Arduino perspective. What I'm using is an ESP8266 based microcontroller. Commonly in Arduino land, people use are Atmega 328 based. So, for example, the Arduino Uno, one of these guys, or a clone of an Arduino Uno. So these are quite big, they're chunky, obviously wouldn't fit in a bin. You could take the chip off. I mean, you could use a smaller PCB with just the necessary chip, etc. and it would fit in, but there's no Wi-Fi on this, there's no network capability, there's no Bluetooth. It's kind of old in a way, you know, it doesn't connect to anything. It's not good for IoT. But one of the benefits of using Arduino is if you make things in the Arduino Ide and using the Arduino libraries, you don't have to worry about changing from one microcontroller to the other as much. It's not perfect, but there's a good chance you can write code for an Arduino Uno, decide you like another microcontroller better or it has more features, and just switch. So you could obviously program all these things using the microcontroller manufacturers' SDKs and their own IDEs or whatever, but Arduino makes it simple to use multiple microcontrollers. So what I'm using for this is an ESP8266. This is not everything you need to run, but you can see this is much smaller. Well, it is everything you need to run, but you need to make it so that you can connect to these things a bit easier. Or I should say these connections are not your normal connections. I think they're called castellated castellations? I don't know. One of those words. And as you can see, they're very small. They're quite hard to solder to. If you make any mistakes, you quite easily can bridge connections. You either make a custom PCB, or you can use one of these little breakout board type things. This, you solder to it, and it has the necessary resistors to boot, and it also brings out the pins a little bit better, and on the back there's a space for a voltage regulator. So the only thing missing really for this is some kind of socket for the power. So probably you would put a micro USB or some kind of USB socket on it, and then you can just easily plug it in via a USB power supply. Hey presto, you've got an IoT device. Pretty good, eh? If you want to have fun trying to make the smallest possible ESP8266 circuit, you can do it. You can make it smaller than this. So here is quite an ugly thing. Pay no attention to the terrible soldering, but this is literally the minimum you need. I just did this as a kind of proof of concept. That's why it's just rough and ready. But if you ignore these wires, one's just a switch to switch into. I can't remember what that switch is for. Ignore the switch. But here's a temperature sensor wired directly in, ugly fashion, and here's the power. So all you need is to plug this into a battery, and that's a really tiny self-contained IoT temperature sensor. Obviously, like I said, it's ugly. I've still got pins connected to it and all kinds of things. I didn't really care about making a mess with this. But one of the other really helpful things about a Wi-Fi connected microcontroller is you can program this over Wi-Fi. So if I plug this into a battery, let's say I plug this into a small battery. There you go. Ignore these other wires. It's actually a smaller footprint than the battery, you can see there. So you can put this anywhere, or you can plug it into the mains, and you can actually update its code over Wi-Fi. I put a little button on here. I don't know if you can see it. This tiny black thing. This tiny black thing here is a button. If you hold that down when you power it up, it goes into programming mode and it becomes available on the network. You can then send code to it remotely. So it saves you plugging something in over and over again to your computer just to reprogram it. Pretty amazing, really. Inside here is basically two chips. One is the microcontroller and one is a flash chip for memory, for storing your program and data. So that's what's underneath this metal shield. This whole device itself is called an ESP12F usually. That's what is referred to as this board, the antenna, the microcontroller, and the memory inside, and a little LED. So it's amazing, really. Amazing what you can fit in such a small package. These are really cool. Definitely, I tend towards wanting to use those now. The downside between one of these ESP8266 modules is, and your more traditional style Uno board or Atmega 328 chip, is you get far fewer GPIOs, and you think you only get one analog pin. Still, you get Wi-Fi. So what a lot of people do is they'll combine these chips together, so they'll make something with both in. So you've got one of these, you want to program it, you haven't set up any kind of cool over-the-air thing like I've done on this one. So how are you programming this the first time? How are you going to do it? The way you do it is via serial. So as you can see on here, I basically have two connections, which are the TXRX, and that allows me to program this. And then you program it using something like a serial USB to serial adapter, this guy. You would use it to program your board. Here you can see I've got it connected to an ESP12F module, which I've attached loads of connections to so that I can put it in a breadboard and play around with it. So that's one of these upside down. Wire it up so I can do awful experiments to it. But you don't want to have to keep messing around with serial programmers, so let's make this easy. If you're going to manufacture something, what you would do is you would use one of these modules. It's already been certified, it's got shielding on it. You would make a custom PCB similar to this, really. Very little needed extra on the hardware side. It's a simple electronics project. So that would be your hardware. But for us, we don't want to keep having to plug in a serial adapter and messing around like that. So, luckily for us, there exists this. These are generally known as the Wemos D1 Mini. And as you can see, it's got the 12F module on it. It's soldered to a PCB. But the extra stuff it's got are the stuff you need to plug into a USB socket and program it. So that's pretty much everything we need on there. It's even got a little reset button should you need it. So this also fits in the bin. So essentially, our hardware is very simple for this, our electronics hardware. This and 4 LEDs and a resistor and some wires. Okay, you've got your Neopixels. What you want to do is you want to line them up so that they are equally spaced either side of the baffles. And if you look on the back, you can see there's a little arrow that tells you which direction to wire them in. So I'll lay them down with the arrows going in the same direction. And space them out appropriately. Use our old friend Bluetech. No, you can't make anything without Bluetech. Now we've got our spacing, we need to connect the wires to them. Here I've got some solid wire. So the reason I'm using solid wire is just to help it keep its shape. You don't have to use solid wire, but it seems a bit more helpful to keep its shape while you're messing around with it. The downside to solid wire is that if you bend solid wire too often, it will break. So it's not good for any flexible use. This I'm using is really for kind of breadboard purposes. So what I'm going to do is just cut the right lengths so I get this fairly neat. I don't know how neat I'll be able to get it since I'm recording on the other side of a video camera and it's in my way. So those are all my excuses for when it turns out to be an awful soldering job. Please leave your complaints about my soldering in the comments below. Okay, these pads are actually tinned, but I might tin them some more. Let's talk about the BinDayCator Kickstarter. One of the things you have to know about Kickstarter is that you lose money immediately from whatever people pledge. So you lose, I can't remember what it is, but once you take off Kickstarter's own fees and payment processing, you lose about 8%, I think it is. So then you have to get injection molding done, which is something I've not done before. What you have to do is you have to design the objects so that they can be efficiently injection molded. And then once you've done that, they make these steel molds of the objects, or the reverse of the object, so that you can injection mold it. Now the thing is, if you get that wrong, as you might do if it's the first time you've ever done it, like say, oh, the holes don't quite line up or something, I don't know, then they have to throw away those molds and make new ones. And those molds would cost about, I don't know, £10,000 or something. I did actually get quotes in. I got quotes in, and what I'm doing here is tinning the pads, by the way, just to make this job easier. They're already slightly tinned, but this big dollop will make it easier to attach wires to. So yeah, so there's the injection molding risk, which is, say you get a set of molds made, say it costs 10k, and you make a mistake and maybe the rework costs 5k. That's 15k gone, and you've not produced anything for anybody yet. Okay, one thing about solid wire is you can't really solder it that easily. Stranded wire is easier to solder for many reasons. Mainly the reason is the strands actually wick in solder, whereas on a solid piece they do not. So the reason behind the Kickstarter was the software all along. The hardware was doable. I think the chance of making a profit was fairly slim. So then you get to the software side. Now I've worked for quite a long time in companies where my job was on a system that was taking data in from one or more systems, doing something with it, making it available to other systems. So I understand how to do it. I understand the ins and outs of it. But I also understand some of the things that are going to take time. There was potentially 400 different systems we're connecting to, i.e. each different console. Potentially screen scraping, PDFs, web pages, JPEGs. It's not a simple data format. So you've got two tasks really. One is try and persuade as many of them as you can to do a simple common standard, so that the BinDayCator can connect really easily to it. And both these things are going to end up happening. You have a layer in between which translates everything for you, and you would have to have a system which checks to make sure it's working. If it's not working, it would flag it up. This happens all the time in companies, overnight systems, jobs fail. It just happens. So you've got an ongoing maintenance job with the BinDayCator platform. Now, there are many ways around it. So one of the things that could work is if a council wanted to provide BinDayCator for its residents, they could allow their residents' BinDayCators to connect directly to that council because it's a known format. It doesn't have to go through this translation layer. So it could work on small scales, and I guess that's what this video is. It's the smallest scale, i.e. you watching this video thinking, I'm going to make one of those. So the middle one doesn't need to be solid core. So I probably won't use solid core for it. I will just use stranded wire, what I've got over here. Ta-da! Fantastic. Is that grey colour? That'll make the video really pop. So essentially the Kickstarter was to test if enough people were interested. If it exceeded its target, then I would definitely have sat down and gone through every council and tried to make it compatible with every council. Obviously people were willing to help. A few people on Twitter reached out saying they'd be willing to help as well, so it probably wouldn't have just been me, but it would definitely have been a goer. And that's one of the good things about Kickstarter. What I didn't want to do was to go to the trouble of making something that people thought was a good idea. You know, on Twitter, there's no cost or effort in retweeting something or liking something, so people do. But just liking something doesn't mean you would be willing to pay for it or it should exist. Sounds harsh, but it's true. I was testing the market really, and if loads of people wanted it, we could definitely make it happen. There would be a translation layer which would solve the recalcitrant councils not wanting to provide nice, simple, open data, and it would work. Okay, so I'm just soldering the stranded one in now using our old friend Blue Tack. We've done the ground, the data. As you can see, they're all in, out, in, out, in, out. So you just basically connect them in series. Now it's time for the power. So the way I'm soldering these is I'm just tacking them to the tinned pads and then adding more solder. So I'm tacking them so they don't move, and then I'm adding more solder. Obviously, when you're done, one thing you need to do is check all the joints. So hopefully these aren't too bad, but once I've done these, I can pause the video and check them. It's actually really bowled over by all the positive responses to the BinDayCator. Pretty much everybody on the thread was really positive about it. They liked the idea, so that was really nice. Thanks, people. Okay, I admit at this point I can't really see what I'm doing. I'm quite far away from the thing I'm soldering. My eyesight's not that good, but they seem connected. So there you go. You'll find some, if you're using Blue Tack, some of it's probably stuck to the lens, so remove that or you'll be confused later because it'll light up blue and you won't know why. You think I'm joking, but that actually happened. So now we need to connect these to our development board. As you can see on the bottom left hand corner, there's a 5-volt pin, a ground, and a bunch of IOs. Now we can't use D4. No, we can use D4, but we shouldn't. The reason is D4 is also the pin that's connected to the onboard blue LED. So what will happen is, if you use D4, you'll see the LED sometimes lit up, which you don't. So we'll use D3 as our signal pin. So we just need 3 connections here, and one of those has the resistor on. The resistor is on the GPIO pin, so the data pin. We're just going to add a resistor to it. By the way, I keep calling these Neopixels. I should probably use the term WS2812 because Neopixel, I think, is a brand name, and when you look for these on eBay, you'll find them described as WS2812s. For connecting these, I'm going to use flexible cable. So what's going to happen is, here's the bin. Baffle goes in, the board's going to sit at the bottom. It goes in this way up with the antenna at the front. There you go, perfect fit. This will go on top. Like that, as you can see, very snug fit, perfectly designed. And this will go in here, so there you go, just a dry fit of the components. You can see how it'll work. It's interesting to consider how the light works once it's in here. So at the top there's the bin lid, which you want this to be lit up really. So what you probably want is the top pixel to be a little bit higher up. As you can see, it goes past the end of the baffle just because it does, and the bottom bit, it'll be somewhat compressed in where you can put it based on the microcontroller underneath it. Let's see how much we need. When this is fitted, this is going to be folded up a bit like that. So that's how much, this distance here is how much you need for a wire, which is not very much. So what I'm going to do is I'm going to just line it up next to it to remind me how much I need. That should be enough. There we go. What I usually do is just twist the ends after you pull this off. Stops them fraying. Okay, that's that one. And the power line. I forgot to have the video camera running while I did the other soldering, so I will just explain it to you. Here is the bottom. Here at the bottom of the LED strip, there's 3 connections: 5 volts, ground, and data. The other thing that's attached to D3 is a 300 ohm resistor. So apart from the power, the only other connection is to D3 using a 300 ohm resistor. I've also added a little bit of tape here just as insulation. You could use heat shrink around the wire or any kind of tape, but it's just to protect from accidental short circuits. The metal case on these is grounded, so you don't want to touch any wires to that or you'll get some kind of short going on. I took special care to make sure that the wires are as short as possible. The reason is not just so it fits in the bin, but also if you have wires looping around and just long wires, you can see them, that they cast a shadow inside the bin, so you don't want that. Okay, so now it can go in through the baffle. Baffle goes this way up. As you can see, it just inserts in through here, and that's going to be used to just keep it in place while we test it. And there's the USB at the back ready to plug in. As soon as you plug it in, you should see a little blue light appear very faintly. You might have seen it flash there. Here's the Arduino Ide. If you look at the port menu, you can see COM9 has appeared. COM9 is the board I've just plugged in, so that's good. Out of interest, the other things you can see, network ports. You may remember earlier in the video, I mentioned you can program ESP8266s over the network using Wi-Fi, and that's what these are. So simple PT is that very small ESP8266 device I showed you earlier. It's a temperature sensor. You plug it into a battery, and you can leave it anywhere, but you can program it anywhere on the network as well. So I don't have to bring it back and plug it into my computer just to change the code on it, which is excellent. That was a diversion. Let's get back to the matter at hand. Okay, so the port's there. We need to change our board to ESP8266 compatible board. Assuming you've never done this before, you won't have support built in, so you'll need to go to the preferences and go into the additional board manager URL that you can see here. And in here you need to add this URL. I recommend Googling this step, partly because the URL may have changed by the time you watch this video and there may be a more recent version. Once you've added that, you'll then find that under board, here it's defaulted to Arduino Nano, but you'll find a whole new section of 8266 modules. The one you want is the WeMOS D1, R2 and Mini. So now we've switched to that. The next thing you need is you need the Neopixel Library. So to do that, you want to go into Sketch, include Library, Manage Libraries, search for Neopixel. And here you can see Adafruit Neopixel. This is the one I've got installed. If you don't have it installed, you'll be able to click this button, Install, and that will add it. As well as the library, it also comes with a set of examples. So we're going to use one of those examples to test our LEDs and make sure the soldering and everything was okay, make sure it works. If you go into File, Examples, and scroll down to Neopixel, Adafruit Neopixel, I recommend opening Strand Test. It's probably the best one for this. So here I have Strand Test opened. It defaults to pin 6. We're using D3, so we'll change that to D3. And we don't have 60 pixels, we have 4. So I'm going to change this to 4. The other thing I recommend doing is commenting out some of the examples in here so that it's not quite as headache inducing. So I would comment out everything except rainbow cycle from the loop method. So just leave rainbow cycle 20 in. And I'm going to hit upload. And there we go. Successfully uploaded. The last message you'll see is flush complete. And if we look at the bin, we can see it's cycling nicely through some colours. That's our way of knowing that it's working okay. Now we've confirmed the electronics are working, we can glue together the bin. When you're making something, unless you're happy with it, it's best to just temporarily tack it together with something like hot glue. So what I recommend is, until you're happy with the lighting pattern and the baffle and everything, just use hot glue to keep it in place. For this bin, I'll be gluing it permanently with epoxy resin, but I'll demonstrate for you using this switched off hot glue gun. Be careful with hot glue, it can burn you quite easily, so this one's not dangerous, it's not switched on. Glue under the top pixel and the bottom pixel. If you want, you can glue the WeMOS board to the wires and the bottom of the baffle, but you'll have to make sure the position is exactly right. I usually just put a dollop of glue on the bottom, and then when you push it into the bin, the glue will stick to the bottom of the bin. Once it's in, make sure that the USB socket is correctly positioned before the glue sets. And finally, to keep the baffle in place, add a small bit of hot glue just at the top of the baffle to keep it at the height that you want. This is a simple model, so you can just glue the lid on top. Add a small dab of hot glue to each corner and press it down, and then if any seeps out, you can just scrape it off with a knife. You'll need a very small amount just to keep it in place for now. You don't have to have the baffle at all inside, to be honest, but if you don't, the colours will wash together and become a bit indistinct. Maybe that's the effect you want though. Okay, now a few words about the printing of the bin. I've just printed this on quite a rough setting, 0.15 layer height. It took about 6 hours to print. I haven't sanded this model at all. It can just about get away with not being sanded. If you do sand it, obviously sand it before you do any of the electronics and glue anything in, because you'll generate quite a lot of dust from sanding. Once that's glued, your bin is complete, at least on the hardware side. This video is getting quite long now, so I'm going to end it here. I'll create another video, part 2, that'll explain how to write the software you need to connect to your console and change the bin's colour. For the competition I mentioned, there's actually 2 bins to win. The first bin has demo code on and is fully assembled. So that's the bin you could see at the start of this video. You can control it using your smartphone or a web browser. Change the colours on it or leave it to cycle through an example month. It's just a demonstration bin. but you can program it with any code you like. You can overwrite the demo code that's on there. To win that bin, retweet my tweet about this video. The second bin you can win is actually a kit. So I'll send you all the 3D printed parts and the components, so a microcontroller, some LEDs and some wires, and you can solder together your own. To stand a chance of winning that kit, subscribe to this channel and leave a comment below about anything. I'm afraid the competition is only open to people in the UK,